Hello everyone, welcome to the video number 9, General Structure of FEA for 1D bar element. My name is Vivek Varkal. So we'll quickly summarize the previous video, okay, where we tried to get FEA solution for a problem of 1D rod subjected to axial force, and we took a 1D example. We actually took two examples. We took one element discretization and two element discretization, and we found the FEA solution for these two examples. And we also have seen how this results FEA solution get closer to analytical solution with the refinement of mesh. Okay, and another thing we have discussed is that FEA solution is a actually discrete function. Okay, the displacement function is for particular element is a discrete function. That means we find the solution only at the nodes. Why discrete function? Because it is easy to program in computer. Okay, and another important aspect of FEA solution is that we only need to find u1 and u2. Okay, the nodal solution are sufficient. Okay, we don't need to find the solution for remaining domain or within element. Okay, we did it only for plotting purpose. So that is a quick recap of previous video. So let's start the topic of today's lecture, that is general structure of FEA for 1D bar element. Okay, okay, so strong form, as you know, AEU double dash plus Q0 equal to 0, and a weak form looks something like this. Okay, here we have also written these two terms. Okay, because we are not going to put boundary conditions now. Why? Because as we said, we are not going to find the FEA solution. Okay, as we did in previous two videos, we are going to find the general structure of FEA. Okay, so what we want, as you know, this is our target. This we have seen in initial two videos. Okay, using structure mechanics approach. So this is the same FEA structure we want to find using FEA method. Okay, so we are not going to use boundary condition and solve the problem. Okay, so let's take the same problem. Okay, 1D rod subjected to axial force of Q0. Okay, since we are not going to assign any boundary conditions, let's keep the rod as a free structure. Okay, and as I said, that is why these two terms are that these two terms we will retain. Okay, so we will start with this weak form. Okay, and as you know, the FEM framework, first we get a strong form, then weak form, then discretized weak form. That means we first discretize the domain into number of finite elements, and we write the discretized weak form. Okay, so let's take for example this we are discretizing into n finite elements. Okay, so let's write this weak form into discretized weak form. Okay, so now discretized weak form. So discretized weak form, as we said, it is a what we do in a discretized weak form is we replace the integral over this domain, okay, into subdomain integrals. Okay, for example, if this domain is L, and let's take this subdomain. For now, let's take all the subdomains are of equal length. Okay, so we'll replace this integral over L with the summation over subdomain integral small l. Okay, so sigma k equal to 1 to n is equal to number of finite elements. Okay, and this capital L, I'll put it as a subdomain length. That means subdomain is nothing but finite element. So 0 to small l a e u dash w dash dx is equal to summation k equal to 1 to n integral 0 to small l w q0 dx plus summation k equal to 1 to n wl pl minus w0 p0. So we have rewrite the weak form as a discretized weak form. Now we want to find the FEA approximate. We want to derive FEA equations. Okay, FEA equations or general FEA structure. Okay, so what we'll do, we'll take a particular element. Let's take this particular element. Let's call it as a kth element, kth finite element. Okay, and as you know, uh, the each element can be considered as a free body. Okay, so I'll take one element, particular element. Let's take the small length element, kth element here, and I will write it as a free body. And this is a q0. So we can write for kth element or any element, okay, or any element, the solution we will assume, as you know, the solution is a first we have to assume the solution using shape functions. So u of x is equal to 1 minus x by l u. So this is a kth node, right? And this will become k plus 1 node. So displacement at kth node is uk, and the next node is uk plus 1. So solution will become 1 minus x by l uk plus x by l uk plus 1. So this is now for any element, or we can say this is a general uh, form we have written, general solution, assumed solution we have written for any element. Okay, and we can say this shape function, you remember we have said earlier u is equal to n1 u1 plus n2 u2. So here nk uk plus nk plus 1 uk plus 1. So nk is nothing but 1 minus x by l, and nk plus 1 is equal to x by l. Okay, and this is a generic representation of our solution. Let's write this is a generic representation of solution. Solution is nothing but u, or we can also call it as a field variable. Okay. Now our weak form, discretized weak form. Okay, here I will take it for kth element. Okay, so it will be for kth element. As you know, this is a summation of over n number of finite elements. So for particular kth element, okay, I will just write it. Okay, it will be a same one, same as a weak form, but instead of capital L, now it is going to be a small l. Okay, so for kth element, our weak form is 0 to L AE u dash w dash dx is equal to 0 to L wq0 dx. Okay, plus, okay, this will be a wk pk. Okay, or no, this will become wk plus 1 pk. So w of k plus 1 pk minus w of k, this is pk plus 1 pk. Okay, now we will, what we will do, this our assumed solution we'll substitute here and find the generic structure, generic FEA structure for 1D bar element. Okay, so we will not put the boundary conditions because we do not want to find the solution. Okay, we want to just get the general form or final form of equation. Okay. So here I will say let's take this is LHS, this is RHS 1, and this is RHS 2, right hand side 2. Okay, so one by one I will no, first I will take LHS is equal to, okay, uh, 0 to L AE u dash is nothing but u k plus 1 minus uk divided by L, right? If I just take derivative of ux, it will be a uk plus 1, or I will say minus uk by L plus uk plus 1 by L, right? So this is what I have written. Similarly, as you know, the weighting function as per Galerkin idea, it is same as solution function or trial function. So u dash and w dash will be of same nature. So wk plus 1 minus wk divided by small l, okay, dx. So these are constant terms. Okay, so the final LHS will be something like this: AE by L uk plus 1 minus uk wk plus 1 minus wk, okay, and derivative of 1 with respect to dx with respect to sorry integral of 1 is going to be x, and when we put x with limit 0 is it is L. Okay, so into L by this L, so both goes, so I will have this only these terms. I'll just rewrite it properly. This L and small l, so this both goes. Okay, so this is LHS. Now I will find RHS1. RHS1 is equal to 0 to L WQ0 dx. Okay, so Q0 W is nothing but WK. It is of same uh, similar form, okay, as UX. So WX is nothing but WK 1 minus x by L plus WK plus 1 x by L, okay, dx. Now just we will do nothing but just will do integration and put the limits. So I will take Q0 outside, so WK, and integral of this is x minus x square by 2L, okay, 0 to L plus WK plus 1. The integration of x by L is x square by 2L, limit 0 to L. Okay. So if I just derive this, what I will get is Q0 L by 2 WK plus Q0 L by 2 WK plus 1. Now we will put RHS1 and LHS in our kth element weak form. Okay, so substitute, okay, not substitute, um, so kth element weak form. Okay, AE by L UK plus 1 minus UK into WK plus 1 minus WK is equal to Q0 L by 2 WK plus Q0 L by 2 WK plus 1 plus this RHS2. Okay, WK plus 1 PK minus WK PK. Okay, so now what I'll do, I'll just rewrite this equation. I will write this equation uh, in uh, in terms of coefficients, which we also did for example 2 in the just last video. So I will write this equation in form of coefficients WK plus 1 and WK. Okay, so I will take the multipliers of these two coefficients. and write the equation. So it is nothing but rearranging the terms. Okay, so if I will write the multiplier of wk plus 1. So it is ae by l uk plus 1 minus uk, and this q0 l by 2 minus q0 l by 2. So this is wk plus 1. Similarly, for wk it is minus ae by l uk plus 1 minus uk minus q0 l by 2 w of k is equal to 0. Okay. Now we will just use the property of w of x. Okay, we said that w of x weighting function is arbitrary and it is non-zero, right? For obvious reasons it is non-zero, so this cannot be 0. Okay, and this wk also cannot be 0, so these two terms are 0. Okay, so a by l, first I will write this term. Okay, yeah, this term. So let's write this term first. A by l uk minus uk plus 1 minus q0 l by 2 equal to 0, and this term a by l uh, minus uk plus uk plus 1 minus q0 l by 2 equal to 0. So we have two equations now. Okay, now what we will do, we'll just write this equation in form of linear algebra. Okay, in form of matrix. Okay, so what we get, um, ae by l, okay, 1 minus 1 minus 1 1 uk uk plus 1, okay, is equal to these two terms on will go on to right side, so is equal to q0 l by, sorry, q0 l by 2 and q0 l by 2. Okay, so we did not consider these two terms. Okay, so here it is no, p plus p k, it should be pk plus 1 and pk. So this is a for k wk plus 1, so this become pk1 pk plus 1, and here it is uh, minus p of k. Okay, so I'll just put it here also, minus p of k here plus p of k plus 1. So q0 L by 2, and we'll also get another vector, that is minus pk and plus pk plus 1. Okay, so I will write it again as a by L 1 minus 1 minus 1 1 uk uk plus 1 is equal to f1 and f2. Okay, so f1 and f2 are nothing but force vectors. Force is at node 1, sorry, it should be fk and fk plus 1. Okay, where f of k is nothing but q0 L by 2 minus p of k, and f of k plus 1 is equal to q0 L by 2 plus p k plus 1. Or we can also say instead of p of k, I will say p of 0 and pl, because k is nothing but corner node. Okay, so we have taken this as a free body. Okay, so 0 to small l. Okay, so kth node is at x equal to 0 and k plus 1 node is at x equal to l. Okay, just for simplification, so I will write it as p0 and pl. Okay, so just now we'll write some observations here. Okay, so the notes, we know p of l is nothing but a. So this is before weak form. We have written this a u dash, okay, u dash at x equal to l, and p0 is equal to a u dash at x equal to 0. Okay, and a u dash is nothing but a du by dx. So it stands for axial force in the bar. Okay, uh, so it is actually internal reaction force, internal reaction force at boundaries. Okay, or we can say due to boundary conditions. So we know, like wherever we apply the boundary condition, for example, if we say, if boundary condition at x equal to 0, if we say u is equal to 0, then at that node we get the internal reaction force. Okay, so we get the reaction force. This we have seen in our hand calculation example, I think in lecture video number 4. So you can revisit that video and check this one. Okay, so these are called, so this is what we wanted to get. These are called final our element level FEA equations, or we can say characteristic equations of 1D bar element. and in this term, in this equation, A by L is nothing but axial stiffness of the rod. We already have seen discussed about these equations previously, so I am not going to touch it again. So this is actually axial stiffness of rod. This complete is element stiffness matrix. This is a displacement vector. Okay, this one is force vector. Okay, so force vector is nothing but external force, this one, external force whichever we are applying, and plus internal reaction force due to boundary conditions. Okay, so we can say Q0 L by 2 is nothing but our external axial force. Now we applied Q0, which is Newton per mm. So this we can say nodal equivalent force. Okay, nodal force equivalent to our distributed applied load Q0. And this particular equation, exactly the same equation we have got using in our first two videos of this series, using solid mechanics approach. There we have just taken single element. So UK was UK and UK plus 1, vector was U1 U2, and force vector was F1 F2. Okay. So now we have understood clearly the final equations. We have got FEA equation using FEA method. Okay, so once we get element level equations, what next? Okay, so this also we discussed in uh, initial 3 to 4 videos. I think, yeah, lecture number 3 and video number 3 and 4. We have discussed about assembly of elements, assembly of 1D elements. Okay, so this procedure remains same. Okay, be it FEA or solid mechanics, it is the same. Okay, what we do first step is we get element level equation. Okay, so we write the element level equations for each element. Okay, if we have n number of elements, then we need to write it for n number of elements. Then we perform assembly of we perform assembly of 1D elements, right? Assembly of these elements. So using when we perform, then we get global system of equations. Okay, which also looks very similar to element level element system of equation. Okay, K U is equal to F. Okay, then once we have global system of equations, we apply loads and boundary conditions and solve the problem. So you can revisit video number 3 and 4 to understand this procedure. So this is the end of video. So I will quickly summarize it. Okay, we wanted to find the general structure of FEA for 1D bar element. Okay, so we started with strong form, then we have seen weak form. We discretize the domain into n number of finite elements. We wrote the discretized weak form. Okay, now what we did, we took a particular kth element. Okay, and draw free body of that element. Okay, and we started finding the FEA equation for this kth element, starting with assumption of solution. Okay, And once we have this solution, assumed solution, we have put the solution, we have put this into weak form. Okay, so we have got this characteristic equation for 1D bar element, okay, which looks exactly same as the one which we derived from solid mechanics principles. Okay. So with this, we'll see you in next lecture. Thank you.